Recording in progress.
Online students, can you hear me clearly? Can everyone hear me clearly? Please confirm with a message. Online students, can you hear me clearly? Can someone please respond with a message? Okay, thank you. So let's start with this session. So I'll first finish one question which I started last week, and I'll move into the I'll move on to the with the new lesson. So that would be the plan for today. As I remember this one, this was, please help me with the values. Okay, this was 20 kilograms as I remember. This was 20 kilograms, and there was something 5 kilogram, right? Moving. It started moving with a velocity of, what was the velocity of this guy? 10. Okay, this one starts moving with at a velocity of 10 meters per second. 10 meters per second. And this is a frictionless system. You can't find friction anywhere in the system. Okay, there's no friction in the system. This one starts moving at a velocity of 10 meters per second. The mass is 5 kilogram and this mass is 20 kilograms. It starts moving in this direction, right? So after this way. Okay, anyways, we can go with any of the directions, and after some time when we look at the thing, it is moving in this direction, right? It's moving in this direction, right? That's okay. So in that case, in that situation, at that moment, what is the velocity of this one? What is the velocity of this one? What is the velocity of this guy? That was the question, right? Okay. So how do we, I mean, it's quite easy. How do we get the answer? You can see there's 5 kilogram, 10 meters per second, and can you see any external unbalanced forces in the system? බාහිර අසන්තුලිත බල පේනවද පද්ධතිය? Any external unbalanced forces on the system? No, right? There are no external unbalanced forces. බාහිර අසන්තුලිත බල නැහැ. So if that is the case, we can apply momentum conservation. ගම්‍යතා සංසිතිය දාන්න පුළුවන් නේද මේ වගේ සිනාරියෝ එකකදී? So the solution is applying momentum conservation law. ගම්‍යතා සංසිතිය දාන එක තමයි මෙතෙන්දී තියෙන ලේසිම solution එක. So I'll first choose a direction. This one, I'll choose this direction, positive direction. So initially 20 kilogram, it's not moving. 20 kilogram is not moving. So momentum of 20 kilogram is 0. ගමතාවේ බිඳුවයි. Plus velocity of 5 kilogram is 10 meters per second. Equals after all the collisions. When I look at the system, okay, after some collisions, some number of collisions, when I look at the system, this 5 kilogram is moving in this direction with a velocity of 10 meters per second. මෙහෙට 10කින් යනවා. Clear? 5 kilogram is moving with a velocity of meters per second. Then if I consider that the velocity of this frame as v, or if the velocity of the frame is v, of this larger box is v, I can write still 20 into v, momentum 20 into v, here minus 5 into 10. Why minus? My positive direction is this. Here the velocity is in this direction. මේ වෙලාවේ ගම්‍යතාවේ තියෙන මේ පැත්තට නේ. ඒකේ තියෙන මේ පැත්තට velocity in this direction. So by solving this, I can get the answer as v equals 5 meters per second, right? V equals 5 meters per second. So what happens is the frame, this box is moving at a velocity of 5 meters per second. Okay, clear? Okay, so that is the answer for this question. And there was a question like, isn't this something like something happening inside? That means, I mean, Ethernet cable. If there's something in the system, I think it's so there was a question like this: isn't this something happens internally? Can something happening internally move us? That means for an example, try to understand this properly, okay? Uh, if there's a truck like this, if there's a truck like this, if there's a person here, if he tries to push this truck, will it move? Will it move? No, right? If we try to push this truck, it will not move, right? Why? What is the reason? What is the reason? Because this is something happening internally, right? Someone can't get inside a system and external force on that system. Is that clear? Okay? This is something happening completely internally. Clear? Okay? Someone can't stay on a truck and push the truck. It's useless, right? It will never happen, right? So the question was, so then how can this system move? This is something happens internally, clear? This is something happens internally. So how can this system move? So the basic idea is, although it looks like an internal something, okay? Although we see that this ball is inside this box, there is no connection between them. There is no connection between them. So when this ball collides with this box, the box will start moving. That means, what is the difference between these two scenarios is, try to understand it properly. Okay, I'll finish this question and I'll move to planar forces. මම එක තලබල පටන් ගන්නවා මේ question එක කරලා ඉවර වෙලා. This person applies a force on the truck. Clear? This person applies a force on the truck. Reaction of that force will be on this person. Clear? Reaction of that force will be on this person. Clear? This is the action. This is the reaction. Now this person should move backward. This person should move backward. Clear? So who stops that? කවුද ඒක නවත්තන්නේ? It's stopped by the friction again. Clear? It's stopped by the friction. The friction appearing here, it stops this person from moving. Clear? Then where can you find the reaction of this friction? It's on the truck. So now see, now consider all the forces on the truck. F and F, what happens? They cancels out. So there is no resultant force on the truck. Clear? So in a situation like this, you can't move the truck. Okay? You can hit the truck, or you can push the truck, you can pull the truck, but I mean, you can try to do everything, but the truck will not move. Clear? Because there's a connection between them through friction. Clear? ඒ දෙන්න අතර සම්බන්ධයක් තියෙනවා ඝර්ෂණය හරහා. Clear? There's a connection between them through the friction. Clear? But in this case, when I tell that there's no friction here, nothing happens. Clear? Tell that there's no friction here. මෙතන ඝර්ෂණයක් නැහැ කියලා මම කිව්වම nothing happens. Clear? Because there's no connection between them. Clear? So this one and this one are almost two separate objects. Clear? So this collision and a collision like this, which happens from outside, are same when there is no friction. Clear? This collision and this collision both are same when there is no friction. Is that clear, everyone? So write this down if you need anything, and I'll move to co-planar forces, but I have to do more questions from force and momentum. So towards the end of the class, I will do more questions from force and momentum too, and when we are doing questions from co-planar forces, I'll be repeating some questions from some concepts that we learnt in force and momentum will be used. So online students, I think you can hear everything clearly and the video is clear, right? If there's any issue for online students, please let me know. Okay, so physical class students, I think you have the note, right? And I uploaded the tute to the group too, and the tute will be available in the Zoom chat in 5 minutes. So online students, you can get the tute through the group or through the Zoom chat. Okay, so I'll start with the lesson co-planar forces. Ekathala bala. Uh, yes, I mean, if you look at the tute, okay, attention everyone. If you look at the tute, there's some part repeating. Okay, I'm not gonna repeat that part. Okay, we learned everything. Okay, we learned a lot of attention everyone. I learned a lot of things. I mean, we learned a lot of things in vectors, right? Shikavaladi. Lot of relationships about vectors. Lot of equations related to vectors, right? Okay. So what are these equations or the rules? One is triangle of forces. Triangle of forces. What is the meaning of a triangle of force? Anyways, it was triangle for triangle, right? It was a vector triangle. That means if we mark two vectors, okay, if we mark two vectors like this, vector A and vector B, you will get the resultant vector, okay, you will get the resultant vector by joining these two lines. Can you remember? You will get the resultant vector by joining these two lines. That was the law, right? Can you remember? So what is the the basic idea behind this is, this is something related to what? This is something related to, this is something related to vectors, but here in this lesson we are talking about forces. But at the end of the day, force is a vector. So whatever the theorems that we learned about forces, about vectors, will be applicable for vectors. Clear? So the vector triangle law, okay, it is vectors, but at the end of the day, force is a vector. So same thing applies here. So I'm not going to repeat everything related to triangle of vectors, you know. So I'll just keep repeating things. Within 10 minutes, I'll repeat all the laws. Then I'll move into actual coplanar forces, new theories related to coplanar forces. Okay. So this is the first part. Then we learned polygon, right? Yeah. Okay. So for online students, is it clear now? Oh, okay. So online students, is it clear now? Online students, is it clear now? Can someone please respond? Okay, so this is a triangle of vectors. Then we learned polygon, vector polygon. What is a polygon of vectors? Daishika bahuvashyak kiyanne mokakda? When there are more forces, I mean when there are few forces like this, 1, 2, 3, or 4. When there are multiple forces like this, okay, you draw the first force, you draw the second force, you draw the third force, you draw the fourth force. Then how to get the resultant? By connecting the starting point and finishing point, you will get the resultant. Clear? You will get the resultant. So this is initially we learned this under the name vector polygon, but now even for forces it is applicable. So this is a polygon of forces. Clear? දෛශික බහුවශ්‍ය කියලා ඉගෙන ගත්ත එක බලවලට apply කරන්න පුළුවන් කෙලීම. Clearද? Because it is again a vector, right? Clear? Then we learned about, so definitely you have to know vectors to understand this. Okay, I'm not going to repeat things because these are the same set of theories which we had in our vector tute. Then we learned something called vector parallelogram. දෛශික සමාන්තරාශ්‍රය. We learned something called vector parallelogram. දෛශික සමාන්තරාශ්‍රය. So what was the idea behind that? If you mark two forces like this using two sides of a vector, using two sides of a parallelogram, okay, if you mark two vectors as two sides of a parallelogram, you will get the resultant vector by this diagonal. Clear? සම්ප්‍රයුක්තය හම්බ වෙනවා මේකෙන්. Clear? But again here it's applicable for forces, right? So when you, instead of any other vector, if you mark forces here, okay, මෙතන බල mark කරොත්, if you mark forces here, you will get the resultant force. Clear? This is how to get the resultant force. And if this force is P, and if this is Q, and if this is theta, what is the equation for the resultant? What is the equation for the resultant force? If it is R, if the resultant is R equals P squared plus Q squared plus 2PQ cos theta square root. Clear? Sorry, if this is theta, sorry. If the angle between those two forces is theta. Can you remember this equation? This one we derived for vectors. It again works for forces. Okay? If this is P, if this is Q, and if the angle between them is theta, R, you can get R by P squared plus Q squared plus 2PQ cos theta. Then if this angle is alpha, angle between the resultant force and P, if this angle is alpha, you can get tan alpha by Q sin theta over P plus Q cos theta. Q sin theta over P plus Q cos theta. Clear? Can you remember these two equations which we learned for vectors? So it again work for forces too. Okay? දෛශික වලට ඉගෙන ගත්ත මේ rules ටික හැමම බලවලට දාන්න පුළුවන්. Clearද? Okay. Then there's a practical. I'm going to skip the practicals and do all the practicals at the end. Okay? Then we again learned how to resolve a vector, right? Or divide it into parts. If there's a force like this, if there's a vector like this, R, if this is theta, what is the component towards this direction? මෙහෙට තිබ්බ component එක මොකද්ද? R cos theta. What is the component in this direction? R sin theta. Clear? So when we learn this for vectors, you can apply it for forces. So all these rules that we learned in vectors, okay, and if someone if someone haven't done these parts, you can always ask for recordings. Okay, all the new students, please stay after the class and join the group, and please ask for the recordings if you have missed anything before this part. Okay, if you have missed any lesson before this lesson, please ask for the recordings. Okay, so because meanwhile, like while I'm teaching, and you can you can use one day per week to cover whatever you have missed. Okay, I'll give you all the recordings up to this point. Then while completing this lesson with me, you can finish the lessons, whatever the lessons that you have missed up to this point, through recordings. Okay, and you can stay after the class and ask whatever the questions that you have related to the recordings or the theory that I teach here. Okay, so is this clear up to now? Nothing new. Okay, nothing new, everything related to vectors. Clear? Okay, so all these theorems that we learned for vectors, we can apply for forces. මේ දෛශික වලට ඉගෙන ගත්ත ඔක්කොම බලවලට දාන්න පුළුවන්. Clear? Okay. Then let's talk about co-planar forces. Actually, here we are going to learn about forces, but since it is very complex to analyze 3D forces, we are only analyzing 2D forces. Okay, 2D forces in the sense, in this lesson, we will talk about forces which exist in one plane. Okay, which exist in one plane. You will not find another force going like this. Okay, then it becomes complex. Okay, you will not find another force moving like this. So that's why we are learning co-planar forces. Okay, ඒක තල බල කියන එක ඉගෙන ගන්න එකයි, because we need to learn about forces, but learning about 3D forces is quite complex. Okay, 3D forces ගැන ඉගෙන ගන්න එක complex වැඩි, so we learn about co-planar forces. Clear? So there's something new, I mean, about forces which is not common for other vectors. What is that thing? There's a property about a force which is not common for other vectors. අනිත් දෛශිකවල නැති බලයක තියෙන ලක්ෂණය මොකක්ද? It has a point of action or a line of action. Okay, there's a line of action. Okay, and I saw this, I mean, in this term test royal paper, you had issue like what will be a null set, right? What was the final answer? There was ongoing discussion about that. What was the final answer? 0, 1 force or 3 forces, so what? What was the final answer? First one or third one? Can't remember, don't know. No? Done. Okay, so the problem there was, first again. So the problem there was, the question in that paper was, this year royal term test, which system of forces, I think, what is the minimum number of forces which can be a null set, right? That was the question. What is the minimum number of forces that can be a null set? That means for the resultant to be 0, okay? For the resultant to be 0, something about forces, okay? Nothing related to coplanar forces, it's about forces. The question was, what is the minimum number of forces required to have a resultant of 0? සම්ප්‍රයුක්තයේ බිඳුවක් වෙන්න තියෙන්න ඕන අවම බල සංඛ්‍යාවනේ. Okay, so the discussion was, I mean, you will learn the answer behind this throughout this lesson, but I mean, I'm not going to talk about 3 forces because we will learn it in this lesson. But what I need to teach is, I think one of the answers given was 1 force. Why? There can be, I mean, what is the minimum number of vectors required to have a resultant 0? That was the question, I think. So one of the answers given was 1 vector. Why? You can have a vector system of 1 vector and it can be 0. And it can be 0, then it is 0. Clear? So basically, if you have a system like this, there are no vectors here. Okay, so it is not basically a vector network, but mathematically it's correct. Why? Something called the 0 vector exists. In a way, something called the 0 vector exists. So if your vector system has a 0 vector, that means actually if your vector system doesn't have a vector, but if your vector system has a vector, if your vector system has a vector which is 0, then the resultant is 0. In a way, it's quite right. I mean, I'm not gonna go through that discussion because I think there's already issues with that, so I'm not gonna interfere with that problem. But the second answer, there was a second answer. Second answer is, I'm not talking about the given answers. Can it be 2 vectors? Can it be 2 vectors? It was something like this. You can have, it may be 2 vectors. Something like this. Okay. So can this be 0? Can this be 0? So there's an issue with this one, okay? There's an issue with this one. Some issue that I see in this system. Why? They were talking about vectors, right? Not forces, right? Vectors, right? So basically, someone asked me, if there are two vectors, okay? If there are two vectors, how do we know whether they are parallel vectors or not? How do you know whether they are in the same line or not? Okay? Why? I'm not talking about the lesson here, okay? I'm just doing a small explanation. If you have two vectors like this, they are not basically two vectors. It is the same vector with the magnitude of v1 minus v2. It is the same vector with the magnitude of v1 minus v2, okay? You can't have two vectors like this. It is this, right? Okay? But can we have two vectors like this? Two vectors like this. Then they will not cancel out, right? If you have, that was the question asked from me, okay? I'm talking about a question asked by a student, okay? If you have two vectors like this, then it will be 0, clear? If you have two vectors like this, then it will be 0. But how do we know whether these vectors are like this? Then they can't cancel out each other, right? But the problem is, there's no point of talking about two vectors like this. Why? A normal vector doesn't have something called point of action or line of action, okay? A normal vector doesn't have something called line of action. So you can't tell that this vector is here. There's no meaning behind that. Why? Only a vector like a force has a line of action, right? Only forces have line of action. So when we talk about other vectors, maybe velocity, you can't tell one velocity is here and other velocity is here, so they will not cancel out. There's no meaning behind this statement, right? There's one velocity here and other velocity here, so they are not in a straight line, so they will not cancel out. There's no meaning behind this statement, clear? Why? There is no line of action defined for other vectors. අනිත් දෛශික වලට ක්‍රියා රේඛාවක් නැතුව කෙලින්ද ඉන්නේ මෙහෙමද ඉන්නේ කියලා දෙයක් කියන්න බෑනේ. So when you talking about other vectors, okay, when we talk about other vectors, okay, there's a problem that you can't discuss about this situation, clear? To discuss a situation like this, the vector should have a line of action or a point of action, clear? So when we talk about forces, if you apply two forces like this, it will rotate. If you apply two forces like this, it will not move. Why? For a force, there's a line of action. බලයකට තියෙනවා ක්‍රියා රේඛාවක්, clear? So when you talk about forces, whether they are like this or like this matters. Whether they are like this or like this matters. Why? If you keep this pencil here and try to push it from two sides, it will not move. If you keep this pencil like this and try to move it from here and here, it will rotate. So when we talk about forces, the placement matters. Why? Because it has a line of action. එයාට ක්‍රියා රේඛාවක් තියෙනවා. Clear? And when you talk about other vectors, talking about a line of action or the placement is useless, right? Okay? You can't tell one velocity is here, other velocity is here. No meaning behind that, okay? එක ප්‍රවේගයක් මෙතනින් යනවා අනිත් ප්‍රවේගය අතනින් යනවා ඒකින්ද ඔය දෙක කැපෙන්නේ නැහැ. ඔහොම දෙයක් නැහැ නේ. So it's something complex that we have to discuss, okay? See, I'm just talking about a question asked by a student, okay? The question he asked me was, if there are two vectors, how do we know whether they are straight line or like this? My answer is, there's no property in other vectors like that, clear? There's no property in other vectors like that. They can't be in a straight line or they can't be like this. Why? There is no line of action defined for other vectors. අනිත් දෛශික වලට ක්‍රියා රේඛාවක් define කරලා නැහැ, clearද? Clear? So it's a different story, okay? Let's discuss that question properly after learning this lesson, okay? But for now, I'll move on. But this is something that you have to understand properly when we are going to talk about forces and vectors. Try to understand the difference, okay? Try to understand the difference, because what happens is here we learn a lot about forces. Then in the A-level MCQ, when they ask something about vectors, you apply this set of theory for vectors and you get everything wrong. Clear? So things you learn in vectors, you can apply for forces. But things you learn about forces, like this line of action, you can't apply for vectors, okay? So properly keep it in mind, okay? Properly understand that whatever you learn here, you can't apply for other vectors. Anit daishika වලට දාන්න එපා, එතනම වරදිනවා. Clear? Okay? Because force is a special vector which has a property called line of action. ක්‍රියා රේඛාව කියලා property එකක් තියෙන special vector එකක් තමයි බලය කියන්නේ. Clear? Is it clear? Is it clear? Okay. I'm not going to talk about that question, but maybe, did you get the marking schemes? No. Will they give you a marking scheme or not? Otherwise, I was planning to do a discussion of that paper and few other papers, few other term test papers from this year. Okay, if you are getting a marking scheme, please let me know, because it's pointless to discuss. If you are getting the marking scheme, you can always check the marking scheme. But if you are not getting the marking scheme, I can do the discussion for few term test papers this year. We'll see. So now we are going to talk about something, okay, something special for vectors, okay, about something special for vectors. Something special for forces. What is that? We can rotate something using a force. We can rotate something using a force. Clear? This property is there because a force has a line of action, okay? That means you can keep this pencil like this, and if you apply a force, what happens? It rotates, right? It rotates. Clear? So definitely this ability to rotate, okay? This ability to rotate, this ability to rotate definitely depends on what? The magnitude of the force. Clear? If you apply a very small force, it will not rotate. If you apply a huge force, it will rotate. Clear? So the ability to rotate a system, it will depend on the magnitude of the force. But there's another thing that decides this ability. What is that? If you try to rotate it by applying the force here, it will not rotate, right? See? If you try to, instead of applying the force here, if you apply the force here, difficult to rotate this thing, right? So this ability to rotate a system using a force, okay? Ability to rotate a system using a force depends on two factors then. What are they? One is magnitude of the force. Clear? One is magnitude of the force. Balaye vishalatwaya. Other thing is the perpendicular distance from the force, from this point to the force L. Clear? So this ability to rotate a system depends on the magnitude of the force, balaya vishalatwayai, and this distance. Clear? And this distance. So we give a name to this property. What is the name? Moment of a force. Balayaka gurnaya. Clear? We give to this property, ability to rotate something, we give a name. The name is moment of a force. Balayaka gurnaya. Moment of a force. Clear? So then if it depends on F and L, what should be the equation for this? If it depends on F and L, what should be the equation for this? Equation for moment is FL. Clear? Equation for moment is FL. Clear? Force into perpendicular distance to the force. Clear? බලය වැඩි කිරීම බලයට තියෙන ලම්බ දුර. Clear? So is this moment, okay, is it a vector or not? ගූර්ණය කියන්නේ බල ගූර්ණය කියලා අපි මේකට කියන්නේ. Is it a vector or not? Vector or scalar quantity? It's a vector, right? It's a vector. So what is the direction? How do you get the direction? If it is a vector, how do you get the direction? By right hand rule. Okay, how? This force is moving in this direction, right? So if your right hand, other fingers of the right hand moves towards the direction of that force, thumb will show the direction of the resultant vector. Clear? That means to get the direction of the moment, okay? To get the direction of the moment, ගූර්ණයේ දිශාව ගන්න, you rotate, you take your right hand and you rotate other fingers towards the direction of the force. Then this thumb gives you the direction of the moment. Clear? ගූර්ණයේ දිශාව thumb එකෙන් හම්බ වෙනවා. Clear? That means this is a vector and vector direction is perpendicular to this plane. Clear? මේ තලයට ලම්බකයි දෛශිකයේ දිශාව. Clear? For maths people, you can definitely understand. What is the reason behind this? What is the mathematical reason behind this? For maths, only for maths people. This is not a this is not a dot product. This is a cross product. Okay? For maths people, moment is a cross product. කතිර ගුණිතයක්. So when you apply a cross product, the resultant is perpendicular to that plane, right? Okay? So for maths people, if you are writing moment, okay? If you are writing moment in a maths paper, you can't write it just like this. It should be a cross product. Clear? ඒක කතිර ගුණිතයක් විය යුතුයි for in a maths paper. Here we only think about the magnitude in physics, so writing it like this is enough. For maths people, if you are writing moment in a maths paper, ගූර්ණය කියන එක maths paper එක ලියනවා නම්, you have to mark this cross. Clear? Because as you know, this thing and this thing are two separate physical quantities, right? මේ දෙකෙන් එන්නේ භෞතික රාශි දෙකක්. In maths, this is a vector, this is not a vector in maths, right? You know that, right? Maths people? Okay. So you have to know these things, okay, if you are doing maths. Anyways, so this is how you get the magnitude of the moment. And it is a vector, එක දෛශිකයක්. How do you get the direction of the vector? Using the right hand rule. Okay. So now you should understand. And what is the unit? What is the unit of moment? ගූර්ණයේ එකක මොනවද? Force means Newton. Length means meters. So the answer is Newton meters. And attention. And so moment is given by Newton meters. So in this situation, you should understand where you apply the force matters, right? See, where you apply the force matters. But in certain situations, I mean, and to rotate the system, it should be connected at some point, right? See, it should be connected at some point to rotate the system, right? Clear? But sometimes you can rotate something even without connecting it. How? You use two forces. Instead of using one force, you use two forces, then also you can rotate the thing, right? How? You apply one force in this direction and another force in this direction. What happens? See? See? It again rotates, right? So in certain situations, instead of applying one force, you apply two forces on the system. පද්ධතිය මත බල දෙකක් ඇති කරනවා. Instead of applying one force, you apply two forces on the system. Then again it can rotate and you don't need to connect it anywhere. Clear? ඒක කොහෙන්වත් connect කරන්න ඕනේ නැහැ. Clear? Here we call this a couple of forces. බල යුග්මයක් කියලා කියනවා. Clear? A couple of forces. That means this thing also can rotate something. That means this thing can also create a moment. මෙයාටත් ගූර්ණයක් හදන්න පුළුවන්. Clear? This thing can also create a moment. But in this situation, equation for moment is, again, you get the value of one force you get the value of one force F, clear, and you multiply it by the distance between these two forces. This is how you get the moment of a couple, clear? බල යුග්මයක ගූර්ණය ගන්න මෙහෙමයි. This is the equation for moment of a couple. This is the equation for moment of a single force. එක බලයක මේ ගූර්ණය මේ බල යුග්මයක ගූර්ණය, clear? Then tell me something like this, just a question, okay? As you see, these two forces should be equal, okay? These two forces should be equal, and these two forces should be parallel, right? To consider them as a couple of forces, බල යුග්මයක් කියලා සලකන්න, okay? These two forces should be parallel, and these two forces should be equal, okay? What will happen if these two forces are not equal? If this is F1 and if this is F2, if this is F1 and if this is F2, what will happen? What will happen to this system? Yeah, in a situation like this, what will happen is, now what is the difference between these two situations? What is the resultant horizontal force on this system? What is the resultant horizontal force in this system? සම්ප්‍රයුක්ත තිරස් බලය මොකක්ද පද්ධතිය? Resultant horizontal force is F minus F, that means 0. Resultant horizontal force is 0, right? සම්ප්‍රයුක්ත තිරස් බලය බිඳුවයි නේ. So that means if you apply F equals ma, 0 equals ma, that means acceleration is 0. So this system will not move linearly anywhere, okay? මෙයාට රේඛීය චලිතයක් ලැබෙන්නේ නැහැ. There is no linear motion, okay? There is no linear motion. It will just rotate, clear? It will just rotate. But if there's a difference between these two forces, what will happen is, now you apply F equals ma. F1 minus F2 equals ma. So acceleration is F1 minus F2 over ma. What happens is, this system will accelerate, okay? So there will be a linear motion, clear? There will be a linear motion. So there will be a linear acceleration of the value of F1 minus F2 over m. There will be acceleration. But you have F2 here. Using a F2 amount of this force, it will again rotate. Clear? That means you can just draw it like this if you like. You can consider this system as F2 F1 minus F2. You can see this system like this. See, now here you have F2. What will happen if you add these two forces? F1 minus F2 plus F2, again F1, right? So what actually happens is, in a system like this, since this is F2, this F2 and a small amount this force will get together and they will rotate the system. Clear? They will rotate the system. But since there's a difference between these two forces, it will give a linear motion. So the system will move while rotating. Clear? System will move while rotating. Clear? These things you have to understand properly when you are, especially when you are doing rotational motion. This Sunday I'm starting rotational motion for the Sunday class. Okay. So if there's any student who need to learn rotational motion, they can join the Sunday class. But Sunday class I'm teaching in both Sinhala and English, and mainly focused in, like, I'm teaching a lot in Sinhala in Sunday class, not like in this class. But if someone can manage that, and if someone need to learn rotational motion from this week onwards, I'm doing that this Sunday. I'm starting this Sunday. So is this clear? And anyways, if you like, I mean, by this fee you can join both the classes. So if you like, you can watch the recording of Sunday class, or if you can join Sunday class online, or you can come to the Sunday class physically. You have all those options. Okay, if you like, you can join both Wednesday and Sunday classes. If you need, you can get the recordings of the Sunday class. Just request. Okay, so is this clear how this motion happens? So forces have the ability to rotate something. Okay, we call that ability moment. Clear? ඒකට අපි කියනවා පූර්ණය කියලා. Okay, just try to quickly try the answer for exercise 3 question number 2. Exercise 3 question number 2, try to get the answer. Then exercise 4. No, first get this answer. Exercise 3 question number 2. I think online students can find the tute, right? Exercise 3 question number 2. Exercise 3 question number 2. I mean main question number 2. Okay, just a simple question. Okay, so this is the system. Here, what is the answer? What is the moment? බලපූර්ණය මොකක් දෙන්නේ? It's 200 newtons into 20 centimeters. Force into perpendicular distance. Then you get force 200 newtons, perpendicular distance 20 centimeters, this is the moment, you get 40 Newton meter. 40 Newton meter. Here in this case, you always have to consider the perpendicular force, okay? You have to consider the perpendicular component, okay? I mean, you have to consider the perpendicular distance. So, this is the line of action of the force. මේ තියෙන බලයේ ක්‍රියා රේඛාව. So, you have to take the perpendicular distance to the line of action of the force. Clear? බලයේ ක්‍රියා රේඛාවට ලම්බ දුර හොයන්න ඕනේ. So, this length is 20 cos 60, right? This length is 20 cos 60. That means 20 into cos 60 means half. That means 10 centimeters. 20 cos 60 means half, that means 10 centimeters. Now you can get the moment, ගූර්ණය ගන්න පුළුවන්. Moment is force into perpendicular distance. බලය වැඩි කිරීම ලම්බ දුර. Force is 200 newtons. Force is 200 newtons. Perpendicular distance ලම්බ දුර 10 centimeter, 10 centimeters. Then you get centimeters, I can convert into meters, 10 to the power minus 2, like in this one. So, I get 20 Newton meters. 20 Newton meters. Then again, attention everyone, then again you can get the resultant moment of a system. Resultant moment of a system. How do you get the resultant moment? Just like when you are what do you do when you are working with several vectors? You just get the vector summation, right? Daishika samprayukte gannawane, vector summation. Just like that, you have to get the vector summation to get the resultant moment, okay? When there's a set of forces, each force create a moment, okay? If there's a set of forces, each force create a moment. හැම බලයම ගූර්ණයක් ඇති කරනවා. So you can just get the resultant moment using vector summation of each moment. Clear? හැම ගූර්ණයම දෛශික එකතුව ගන්න පුළුවන්. And again here, this answer is not complete. Why? We are talking about a vector. So the direction should be defined, okay? දිශාව define කරන්න ඕනේ. So what is the direction? What is the direction? See, right hand rule, force moves in this direction, so the vector direction is this, right? It's moving towards the board. When something moves towards the board, you can mark it like this. When something moves out from the board, you can mark it like this. Clear? So here it's moving like this, it's moving toward the board. Here also it's moving towards the board. So now this is a complete answer. Without the direction, it is not complete, okay? And attention, and even in these questions, in many of the questions, we usually don't mark the force like this. Even marking the moment like this is enough, okay? In many cases. Try to understand this properly. If they specifically ask you for the direction, if you mark it like this, it's wrong, okay? Why? This is the proper vector direction. මේක තමයි හරි දෛශික දිශාව, right? But assume that taking the moment is just a part of the question. You have to find angular acceleration or something like that, okay? It's just a part of the calculation. So just to mark the direction that you consider, you can mark it like this. If you mark it like this, whatever the forces in this direction are positive, whatever the forces in other direction are negative. Clear? So when you are writing something on paper, this symbol is enough, okay? Presenting the direction like this is enough. But if they specifically ask for the direction, then this is not the answer. It should be like this. Clear? Okay. Okay. So as I said, what can we do then? When you have a network of forces, what can you do? F1, L1, F2, L2, F3, L3. What is the resultant moment here? මෙතන සංප්‍රයුක්ත කූර්ණය මොකක්ද? First, write the point, okay? Write the point. Why? You have to tell in these questions we are only talking about moment, okay? So in such cases, what is the point? It doesn't matter, okay? But when we start working on proper questions, attention, when we start working on proper questions, sometimes you have to take the moment around this point. Sometimes you have to take the moment around this point, okay, in a vehicle. Sometimes you have to take the moment around this point. So you have to define the point that you are considering the moment, okay? So here I'm taking the moment around point O, clear? මම O ගේ වටේ ගූර්ණ තමයි ගන්නෙ, clear? So I write O. I'm considering point O. Then I have to choose a positive direction. I'll choose this direction as positive. Clear? I mark the positive direction. ධන දිශාව mark කරනවා. Now I can write the moment. දැන් මට ගූර්ණ ලියන්න පුළුවන්. This F2 is in that direction, right? F2 is in that direction. So F2, L2. But F1 is in opposite direction. See? F1 is in opposite direction. So minus F1, L1. Then again F3, L3, opposite direction. So minus F3, L3. So this is the resultant moment. සංප්‍රයුක්ත කූර්ණය එන්නේ මේ විදියට. Clear? You mark the point, you provide the direction, then you do the calculation. Clear? ඔන්න ඔය විදියට අපිට final answer එක ගන්න පුළුවන්. When you are considering a moment. කූර්ණයක් ගත්තී. Quickly try. We are not going to move into difficult questions, but I'm just doing some easy questions to for you to understand the equations and all. Try exercise 4. Try exercise 4. Question number 2. Sorry, question number 4 and 5 quickly. Question number 4 and 5 quickly. Try these two. Try to get the answers quickly. Just take, you can just take 2-3 minutes and get the answer, okay? These are not difficult questions. We are just using the equations that we learnt, okay? මේ දැන් ඉගෙන ගත්ත සමීකරණ දාන එක කරන්නේ. Quickly calculate. Just take 1 or 2 minutes to get the answer. So 2 meters are marked like this, okay? Other 2 meters mark වෙන්නේ මෙහෙම. Question number 4. I'll draw the system. You have O here. This is 2 and this is 2. Here you have 4 newtons. Here you have 8 newtons. Here 6 newtons. Here 20. Here 4 here there's no force in this direction, right? This is the system, right? They haven't given a magnitude for this force, so we can just consider this set of forces. This angle is 30. Then question number 5, this one. So this system, consider O, point O. I'll choose this as the positive direction. මම මේ පැත්ත ධන දිශාව කියලා ගන්නම්. First this one, 4 newtons. 4 newtons. This length 2 cos 30. This length 2 cos 30. Then 8 plus 8, same direction, plus 8. Distance, perpendicular distance 4 cos 30. 4 cos 30. This 6 newtons, it's rotating in opposite direction. See, it's rotating in opposite direction. So minus 6 length. What is the perpendicular distance? This one, right? Perpendicular distance is this one. That means 4 sin 30. 4 sin 30. 4 sin 30. What about 20? You don't have to think about 20, right? Why? Plus 20. What is the distance to 20? 0, right? Distance to 20 is 0. Clear? So you will get the answer like this. Clear? You will get the answer like this. Just a question that I'm asking. Have you learned about pressure in O-level syllabus? Pressure. So do you know things like pressure is always perpendicular to a system? No, nothing like that, right? Okay. No, I was just going to mention something related to moment, a practical point. But we will have to wait until hydrostatics. Okay. I'll teach that when I properly explain what is pressure in hydrostatics lesson. So this system. So attention, in certain cases, okay, in this situation, you know the perpendicular distance to this one, right? It's nothing new, okay? You know the perpendicular distance to this one. It's not difficult, clear? But you have to find the perpendicular distance to this one, right? මෙයාට ලම්බ දුරත් හොයන්න ඕනේ. See, you have to find the perpendicular distance to this one, clear? In some cases, it's not that difficult. It's not that easy. Here it's easy, yes, okay? Here it's not difficult, but finding the perpendicular distance to this line, in some questions it will be difficult. In such cases, what you can do is, you can resolve the vector into two directions, right? දෛශිකය දෙපැත්තට බෙදන්න. That means, what is 20? Instead of 20, you can write 20 cos 30 in this direction, 20 sin 30 in this direction, and you can forget about 20. Clear? In a situation like this, you can just resolve the vector and forget this one. Clear? Okay? I get two components of the vector, 20 cos 30, here 20 sin 30. Clear? Now what can I do? දැන් මොකද්ද කරන්න පුළුවන්? I'm gonna write moment around point O. This is my positive direction. මේක ධන දිශාව. Attention. This is my positive direction. So 5 Newton, M equals 5, length 4 plus 10, length 8, 5 into 4 plus 10 into 8, clear? පහ වැඩි කිරීම 4, මෙතන 10 වැඩි කිරීම 8, clear? Here, first let's try 20 sin 30. This is rotating in this direction, 10 is rotating in this direction, but 20 sin 30 is in opposite direction, right? It's trying to rotate the system in opposite direction, clear? So it should be minus, it's not trying to rotate the system in this direction, it's trying to rotate the system in other direction. So minus 20 sin 30 into this distance, clear? 20 sin 30 into 8. Here 20 cos 30, it's moving through point O, right? 20 cos 30, it's just moving through point O. So what is the perpendicular distance to 20 cos 30? 0, right? Why? This is 20 cos 30. This is the line of action of 20 cos 30. So 20 cos 30 is moving through O. 20 cos 30 යන්නේ O හරහා. So the moment it generates is 0, clear? එයා හදන ගූර්ණය බිඳුවයි. Because there's no perpendicular distance between the line of action and the point, clear? මේ ක්‍රියා රේඛාවයි OI අතර දුරක් නැහැ, clear? So it's 0, so you get the answer like this. මේකෙන් answer එක ගන්න පුළුවන්. Clear? Okay. So write this down quickly. I'm not going to do any difficult questions now. First, we will understand a set of theory points, and we will learn up to center of gravity today. As soon as possible, we will learn up to center of gravity. Then we will combine everything and do some difficult questions, difficult and nice questions. Okay? මොකද්ද තන ප්‍රශ්නේ? මොකද්ද කරදර කරනවා? Pressure 5 into 4, 10 into 8. Why? තව 10ක් තියෙනවානේ. Yeah. This one, right? නෑ එයාවත් මාක් කරලා තියෙයි. What is the issue? Sorry? attention, here this is 4, perpendicular distance to line of action is this 2 cos 30. This is 8, perpendicular distance to the line of action is this, right? 4 cos 30. This is 6, perpendicular distance to the line of action is this. Clear? Perpendicular distance to its line of action is this. What is the value? 4 sin 30. Clear? 4 sin 30. Clear? Is it clear, everyone? Okay. Now by combining these things, we are going to learn a theorem. Now we are going to this is just the, I'm not doing a lot of questions at the moment because we have to do a lot of questions after learning these theory parts. So attention everyone. Now by combining these concepts, okay? By combining these concepts, we are going to learn about something pretty important, that is a law, a theorem. We call it principle of moment, Gurna Mula Dharma. Okay? It is principle of moment, Gurna Mula Dharma. What is the what is this law? Consider this point as O. Attention. Consider this point as O. Assume, there may be lot of forces here. 10 Newton, 15 Newtons, 5 Newtons, like this. Okay? Attention. Okay? 10 Newtons, 15 Newtons, 5 Newtons, you have lot of vectors like this. Clear? So, what is the resultant of these vectors? What is the resultant of these vectors? මේ දෛශිකවල සම්ප්‍රයුක්තය මොකක්ද? 10 plus 15, 25, 25 minus 5, 20, right? Resultant of these vectors, මට ඔය මැද්දේ කතා කරනවා එහෙනවා අහගන්න. 10 plus 15, 25, 25 minus 5, 20. Clear? So, resultant force is 20 newtons, but there's an issue. This is not a complete answer. We know the magnitude, 20 newtons. We know the direction, downwards. But why isn't it complete? We are talking about a force. A force is meaningless without the line of action. So, when we try to find the resultant force, සම්ප්‍රයුක්ත බලය කියන එක හොයද්දී, when we try to find the resultant force, giving the direction and magnitude is not enough. You have to tell where is the line of action of the resultant force. Is that clear? සම්ප්‍රයුක්තයේ ක්‍රියාරේඛාව තියෙන්නේ කොහෙද කියන එක කියන්න ඕනේ. That means this is the resultant, 10 plus 15 minus 5. This 20 Newton, whether it's here, whether it's here, whether it's here. See? You have to just find in the resultant is not enough. You have to find its line of action. Otherwise, it's not a complete answer. Okay? So, we can use this principle of moment. Gurna Mula Dharma කියන එක පාවිච්චි කරන්න පුළුවන්. We can use principle of moment to find the line of action of a resultant force. How? සම්ප්‍රයුක්ත බලයේ ක්‍රියාරේඛාව හොයන්න අපිට ගුර්ණ මූලධර්මය පාවිච්චි කරන්න පුළුවන්. How? Principle of moment is sum of each moment of a system is equal to the moment of the resultant force. පද්ධතියක එක් එක් ගූර්ණවල VG ඓක්‍ය සමානයි සම්ප්‍රයුක්ත ගූර්ණයට. Clear? Sum, algebraic sum of each moment of a system of forces is equal to the moment by the resultant force. That means, now I'll consider point O. I'll choose this as the positive direction. If this length is 2, if this length is again 2, then again if this distance is 2, I can write 10 into 2 moment 10 into 2 plus 15 into 4 15 into 4 minus 5 into 6 5 into 6 minus 5 into 6. Clear? This is the sum of each moment. Gurnawala ekatuwa. And principle of moment tells Gurna Mooladharma kiyanne this is equal to the moment by the resultant force. Samprayukte Gurnata samanai. That means if the moment is acting at this point, if the moment is acting at this point, 20 newtons, if it's acting here, clear? If it is acting here, if the distance to that 20 newtons resultant force is x, okay, what is the moment by the resultant force? 20 into x. 20 into x. Now you can get the answer. What is the value of x? X kya mokakda? Sorry? 2.5. X is 2.5 centimeters. That means now I have the complete answer. Resultant is 20 newtons downwards and it's acting at 2.5 centimeters from point O. Clear? Now this is a complete answer. May the sampurna uttaraya. Okay, anyways, if these are centimeters, then this is centimeters. If these are in meters, this is in meters. Okay. So, is it clear? Centimeters or meters. So, let's write it as meters then. If everything is in meters, answer will be in meters. If 2 is meters, then this 2.5 is meters. Is it clear? This is principle of moment. Gurna Mooladharma. Clear? I mean, I'm not teaching exactly in the order of your tute, okay? This time I have changed the order because to make it more clear, okay? To make it more clear, I'm changing the order a bit. But anyways, you can find everything that I'm teaching and everything that I'm writing in your note, okay? So just go home and go through the note a bit, okay? I'm not exactly teaching in the correct order, but everything is included in your note, so you don't have to write anything, okay? For now, you don't have to write anything. Now, this principle of moment, attention everyone, this principle of moment gives us very important result, or this resultant force concept about the resultant force gives us a very important result, that is the concept of center of gravity. ගුරුත්ව කේන්ද්‍රය කියන සංකල්පය එන්නේ මෙන්න මේක හින්දා. Clear? Center of gravity. What is center of gravity? Is it clear up to this point? Is it clear? Okay, we will do some questions, but before I have to finish these theory parts. So, because it's more like a story, so we have to. I'll just go with the flow. So, this principle of moment, me Gurna Mooladharma, it using that we defines a very important point, center of gravity. What is center of gravity? Center of gravity is the place where the total weight of a system is combined. Is that clear? That means, now here what we did was, there was a set of forces, okay? Attention, there was a set of forces, and this is the place where the whole force resultant is acting. Clear? Now consider a rod like this. Consider a rod like this, okay? A metal rod, okay? Now, you divide it into small parts, okay? Or any object, okay? Let's consider a very uneven object like this. Now you break it into small parts. You break it into small parts. Now I'll take this point as O. If the mass of this point is m1, weight is m1g. If the weight of this point is m2, mass m2g, m3g, m4g. If the total mass is capital M. If the total mass is capital M. Now, when you consider all these small weights, they combined, they create a weight of mg. Clear? When you combine all these small weights, it creates a capital mg weight. Okay? Now, when you apply principle of moment to this system, මෙයාට ගූර්ණ මූලධර්මය දැම්මම, that means you do the same thing like in previous question to each weight of the system. If you consider this table, you apply the principle of moment for each particle of the table. Then you will be able to find a point where you will be able to find the point of action or the line of action of this capital Mg. Is that clear? Just like in the previous question, okay? If you do the same to a system, a natural system, okay? If you do the same to a natural system, okay? You will be able to find the line of action, distance to the line of action of the resultant weight. That means this is the point where whole weight is acting. මෙතනින් තමයි මුළු බරම ක්‍රියාත්මක වෙන්නේ. Clear? This point, what is the name given to that point? Center of gravity. ගුරුත්ව කේන්ද්‍රය. Clear? So center of gravity is just a mathematical definition. What is the meaning of that? The place where the whole weight of a system is acting. Clear? So to balance this system, okay, if you can apply a force just under this point upwards, it will be balanced. Like you can balance anything from one point, right? You can balance anything from one point. How? Because if this is the center of gravity of the system, whole weight is acting from that point. If you can keep your finger just under that point, you can balance the point using the center of gravity. Is that clear? So this is the concept of center of gravity. ගුරුත්ව කේන්ද්‍රය කියන්නේ මෙන්න මේ සංකල්පයට. Clear ද? So we started with moment, okay? Then we moved into principle of moment, ගූර්ණ මූලධර්මය. Then using the principle of moment, we define something really important, that is the center of gravity. Is that clear? Okay. So okay, attention. You have a system like this. Attention. This plane is like this, okay? This plane is like this. XY, X is in this direction, Y is in this direction. Clear? X is in this direction, Y is in this direction, okay? You have a non-uniform system like this. This non-uniform system contains 6 kilograms here, 4 kilograms here, 5 kilograms here, and 8 kilograms here. This distance is 2 meters. This is 6 meters. This is 3 meters, this is 8 meters. Find the center of gravity of the system. Paddhati Gurutva Kendra hoyan. Find the center of gravity of the system. Find the point. Find the center of gravity quickly. Gurutva Kendra hoyan Paddhati. So just try to understand this system is like this, okay? It's this plane. X is in this direction, Y is in this direction. So weights are acting like this. Clear? Weights are acting like this. Six kilograms, 5 kilograms, 4 kilograms, and 8 kilograms. Sorry, you need an need the x coordinate of 4. So just take it as 3. After this question, try exercise 8. Exercise 8. Question number 2. Question number 3. Question number 6. Yeah, try these 3 questions after this one. Question number 6 and question number 9. I'll give you some time to try these questions. Okay, so how do we get the answer? How do we get the answer? I gave you a set of questions because in A levels it's a very common question to find the center of gravity. I mean, usually everywhere, attention everyone, usually everywhere you get at least one question to find the center of gravity. ගුරුත්ව කේන්ද්‍රය හොයන්න අඩුම තරම එක ප්‍රශ්නයක්වත් එනවා. So here, how do you find the center of gravity? This is a 3D system, so you have to find the center of gravity twice, right? ගුරුත්ව කේන්ද්‍රය දෙපාරකට හොයන්න වෙනවා. That means, what is the sum? Attention. What is the sum? What is the resultant mass or weight? Let's talk about weight. 8, 8, 4. It's 23 kilograms, right? It's 20, attention everyone. It's 23 kilograms. That means, when this mass combined, it's 23. Clear? මේ ටික එකතු වුණාම 23යි. Now what can I do is, I'll first work in this direction. That means I will consider, now I have to find 2 points. I have to find the x coordinate of 23 and y coordinate of 23. Okay? Then I can find the real center of gravity. Clear? So first of all, I will consider the distance from y-axis. I will consider the distance from y-axis. I'll choose this as the positive direction. Then I can see 5. What is the weight of 5 kilograms? 50. That means 5g. 5g. Plus, it's downwards, 6g. Sorry, I have to multiply it by the perpendicular distance. What is the perpendicular distance to 5g? එයාට මේ axis එකේ ඉඳන් දුර, what is the perpendicular distance from this axis? 2, right? Perpendicular distance from this axis is 2. Clear? 2. Plus, then comes 6. 6g. What is the distance? 6. Then comes 4g. Distance 3. Then 8g. Distance from y-axis 6. Now, principle of moment, ගූර්ණ මූලධර්මය. This sum of these moments should be equal to the moment of the resultant force. What is the resultant force? Resultant weight. සම්ප්‍රයුක්ත බලය මොකක්ද? 23g. 23g. What is the distance? X. By solving this, you will get the distance to distance x. That means you get the distance of the center of gravity from y-axis. How far the center of gravity from y-axis? Clear? So what is the answer? Can someone tell? 4.06. Others? Any confirmations? 4.06. Okay, nice. X equals 4.06. Attention. Attention. Now, distance from x-axis. Now, distance from x-axis. Distance from x-axis. Five g. Distance is 3. 5g. Distance is 3. Plus 4g. Distance is 8. Plus 6g again. 6g. Distance 3. Distance from x-axis 3. Plus 8g, distance 8 equals what? What is the resultant weight? 23g into this length, I'll take it as y. What is the answer for y? 5.6 1 5.6. Okay, so now what actually happens is, attention everyone, xy axis, this is your uniform object. You can find its center of gravity. Attention, you can find its center of gravity here. එයාගේ ගුරුත්ව කේන්ද්‍රය මෙතන තියෙනවා. Clear? You can find its center of gravity here. What is the distance from y axis? 4.06. What is the distance from x axis? 5.6. Clear? Clear everyone? Attention. Attention. This is the location of the center of gravity. මේ තියෙන ගුරුත්ව කේන්ද්‍රයේ location එක. Clear? That is how you find the center of gravity of a 3D system. Clear? 3D system in the sense actually it's in a plane. It's like if this is the plane, if this is the object, I have to find the center of gravity of that object. I mean, since this is more like one dimensional, I can find the center of gravity in this line. But if I'm going to find the center of gravity of this iPad, okay, if I'm going to find the center of gravity of this iPad, I have to find what is the center of gravity in this direction and what is the center of gravity in this direction. Then I have to find the point. That's what I did here. Clear? Clear everyone? Okay. Now you should focus on this thing. Okay. You can cancel out g. Attention everyone. You can cancel out g. Why? There's no point of writing g, right? Okay. Okay, you can write it later. Just focus here. You can remove this g. There's no point of writing g. Why? It's common to the whole equation, right? Okay. It's common to the whole equation. Now, if you remove g, it becomes 5 into 2, 6 into 6, 4 into 3, 8 into 6, 23 into x. In that case, you are not considering the weight. If you write the same equation without g, okay, you are not considering the weight. බර නෙමෙයි consider කරන්නේ. You are considering only the mass. ස්කන්ධය. Clear? Clear? If you write the same equation without g everywhere, okay, you are considering only the mass. Clear? In that case, you can still find x and y, and name given to that point is center of mass. Skandha kendraya. Clear? So if you do the same process that you do to find the center of gravity without considering g, g wa liyanne nathuwa gurutwa kendraya hoyana samikaranema liwuwot. Clear? And using that, if you find x and y, then you get what? Center of mass, skandha kendra. Clear? So it's nothing new. Okay? It's the point that whole mass is centered. Clear? That's what we call center of mass. Now you should understand, if you with g or without g, you get the same answer, right? Okay? With g or without g, you get the same answer. Okay? Then that means there's no difference between center of gravity and center of mass, right? With g or without g, you will get the same answer for x and y. That means there's no difference between center of gravity and center of mass. ගුරුත්ව කේන්ද්‍රයේ ස්කන්ධ කේන්ද්‍රය අතර වෙනසක් නැහැ නේද එහෙම ගත්තොත්? Clear? But there's a difference in some situations. If you consider this iPad, its center of gravity and center of mass are at the same place. If you consider the smart board, its center of gravity and center of mass are at the same place. If you consider this building, its center of mass and center of gravity are almost at the same point. But if you consider maybe Mount Everest, okay, if you consider a mountain, huge mountain, its center of gravity and center of mass are not at the same place. For smaller objects, center of gravity and center of mass are at the same place. ගුරුත්ව කේන්ද්‍රය සන්ද කේන්ද්‍රය එකම තැන තියෙන. But for huge objects like this, center of gravity and center of mass are not at the same place. What is the reason? G changes with height. What is G? Gravitational acceleration, ගුරුත්වජ ත්වරණය. Okay? So when you consider this iPad, it's same gravitational acceleration everywhere, same G everywhere. So you can cancel out G, then you get the same answer. But attention, if you apply same concept for Mount Everest, here it's M1 G1, here it's M2 G2. Why? As you know, gravitational acceleration decreases with the height, right? Okay, when you are so far from Earth, gravitational acceleration, ගුරුත්වජ ත්වරණය, it's really low, right? Clear? So if you have G1, G2, G3 values everywhere, then the equation that you write would like M1 G1 plus M2 G2 plus M3 G3 plus capital MG or something like that. Now can you cancel out G? No. Now M1 G1 into X1, M2 G2 into X2, M3 G3 into X3, Mg into X. Clear? Now you will get an answer for this value X. Attention. Now you will get an answer for X. What is that X? Center of gravity. Now I write the equation for center of mass. X1 M1 plus X2 M2 without G plus M3 X3 equals Mx. Here you can find X, that is center of gravity. Clear? Why you are considering G? Make you attend ගුරුත්ව කේන්ද්‍රය, center of gravity. Here you write the same equation without G, without considering G. Then you get center of mass, ස්කන්ධ කේන්ද්‍රය. Now these two are not equal, right? Now these two are not equal. Why? It's G1, G2, G3, G. Clear? It's different from point to point. So center of mass and center of gravity are same everywhere usually. Clear? ගොඩක් වෙලාවට ගුරුත්ව කේන්ද්‍රයේ ස්කන්ධ කේන්ද්‍රය එකයි. Why? It's around gravitational acceleration around here is, it's like 9.8. If you go 100 meters above, it will also something around 9.8. But if you move 1 kilometer, then it starts changing. So for smaller objects, okay, smaller in the sense it doesn't have to be this pencil or something like that. Even for this building, center of mass and center of gravity are almost same. ස්කන්ධ කේන්ද්‍රය ගුරුත්ව කේන්ද්‍රය එක තැන වගේ තියෙන. Clear? But in situations where G changes, gravitational acceleration, ගුරුත්වජ ත්වරණය වෙනස් වෙන තැන්වල, in such situations center of mass and center of gravity are different. Clear? So as I always explain, to get a B or C a result like that, all you need to know is how to do the calculation and get the answer. But for an A, you must have a really good clarity about these definitions of things. Okay, what is center of gravity, what is center of mass, how do they change? Okay, you must have a very good understanding about theory to go for an A. Okay, that is the difference. Okay, so we usually give interval at this time, right? Yeah. So I'll allow you to do these questions after that. Exercise 8, 2, 3, 6, 9. Exercise 8, 2, 3, 6, 9. Now after interval I'll be doing a lot of questions only, most probably, because we did a lot of theory parts. I didn't do much questions because I need to keep the flow. Okay, everything is connected with every point. Okay, so it's good to finish everything together. So now try these questions, exercise 8, 2, 3, 6, 9, and your revision tubes will be available. uh, I'll provide that, and your papers will be available after the class. Okay, model paper 2, right? Model paper 2 or 3, I can't remember. This week's model paper will be available after the class. Okay, so it's 10 past 5. Interval will be until 5:25. 5:25. Clear? Take the interval, then do these questions. හොඳයි. මම මේ questions ටිකත් ඔයගොල්ලෝ try කරා ඇති කියලා හිතනවා බලන්න. Question number 2369. එතකොට අහගන්න ඉක්මනට ඉඳ ගන්න. හොඳයි අහගන්න. Question number 2. ඒ කියන්නේ අහගන්න. දැන් මේ A levels වල එන ගොඩක් common question type එකක් තමයි මේක. ඒ කියන්නේ අර calculations කරලා center of gravity හොයන්න දෙයක් නැහැ. center of gravity එක කියන්නේ rough judgment එකක් තිබ්බනම් ඇති. clearද? calculations වලින් center of gravity හොයන්න දෙයක් නැහැ. අපිට center of gravity එක ගැන rough judgment එකක්. දල අදහසක් තිබ්බනම් ඇති. ඒ කියන්නේ මොකක්ද? දැන් මෙයාගේ center of gravity කොහෙ තියෙයිද? මෙයාගේ ගුරුත්ව කේන්ද්‍රය කොහෙ තියෙයිද? පොඩ reason කර යන්න පුළුවන්. Okay. Attention everyone, attention. Okay. So, how can we find the center of gravity in a system like this? You can just reason for the center of gravity. You don't have to like do a specific calculation. I mean, you will get different types of questions in A levels, but usually in many questions you don't have to do all the set of calculations, okay? What you have to do is just get a rough idea about the placement of the center of gravity, then because most of these questions are MCQs in A levels usually, clear? Most of these questions are MCQs. So, how can you get the center of gravity of this system? Where can you find the center of gravity of this part A? Where can you find the center of gravity of this part? Around here, right? මේ වගේ හරියක නෑනේ. Center of gravity is placed here. Clear? Then where can you find the center of gravity of this part? මේ part එකේ center of gravity කොහෙද? Around at the center, right? If it is uniform at the center, right? In a uniform object, you can find the center of gravity at the middle, right? That's the usual convention, right? If this was uniform, center of gravity must be in the middle, right? So, now where can you find the center of gravity of the resultant system? Samprayukta paddhati gurutva kendra. Where can you find the center of gravity of the resultant system? This one and this one looks same, right? Okay. So, if the mass of this part is m, that m is centered here now. Is that clear? If the mass of this part is again m, that m is centered here. Okay. Now where can you find the resultant of these two? At the center, right? That means here. This m and this m is centered here, 2m. Clear? So the result center of gravity will be around here. Is that clear? Is that clear? So in many cases or in many questions, you don't need to do a specific set of calculations to find the center of gravity. ගුරුත්ව කේන්ද්‍රය හොයන්න සුළු කරන්න ඕනේ නැහැ. Attention. Okay. What you have to do is just try to have a rough idea about the placement of the center of gravity. Clear? ගුරුත්ව කේන්ද්‍රය මෙතන ඇති කියලා assume කරන්න try කරා නම් ඇති. In many MCQs, A level MCQs. If we try question number 3. These three parts, they almost look like the same, right? So I can assume mass of this part is m, mass of this part is m, mass of this part is m. Clear? Okay. Now, where can you find the center of gravity of this part, this rod? At the center, right? Where can you find the center of gravity of this part? Again at the center, right? Where can you find the center of gravity of this part? Here. That means this M is centered here. This M is centered here. This M is centered here. Clear? So, if I consider these two only, where can you find the center of gravity of this part and this part? මේ දෙන්නගේ common point එක මොකක්ද? Where can you find the center of gravity of this part and this part? At the center, right? At the center. So, 2m. 2m. Clear? Attention. 2m. Clear? Now, where can you find the center of gravity? Now, this part and this part, I can forget these two. Why? Their center of gravity is here. Clear? 2m is centered here. Now you have this rod, mass is m. මේ rod එකේ ස්කන්ධය m. You have these two, center of gravity is here, 2m. Clear? Now where can you find the resultant center of gravity? It must be in this line, more towards close to 2m, right? Close to 2m. Clear? Why? If the weight at one side is higher, center of gravity goes towards that side, right? I mean, if you do a proper calculation, attention, if you do a proper calculation, if this is L, if this is L, I have M here, I have 2M here, this length is L, where can you find the center of gravity or center of mass? ස්කන්ධ කේන්ද්‍රය හරි ගුරුත්ව කේන්ද්‍රය හරි. I'll consider this point, I'll take this point as O. And I'll write the center of mass equation. Center of mass equation. 2m, what is the distance to 2m? L plus m, what is the distance to m? 0. Distance to m? 0. Clear? What is the resultant? 2m plus m? 3m. What is the distance to 3m? X. What is x? 2l over 3. 2l over 3. That means if this is L, 2l over 3 is here, right? More towards this side. So you can find the center of gravity here. So you always have the option of doing a calculation, okay? You always have the option of doing a calculation. සුළු කරලා හොයන්න පුළුවන්. But for many MCQ, especially in A levels, having a rough idea about the center of gravity, where it will be situated, okay, based on the conditions given. Having that rough idea is enough to go through many MCQs, okay. Just like this, you always have the option of doing a proper calculation, okay. Okay. But I mean, it's not necessary. Clear? It's not necessary in many questions. But all you have to do is just try to have a rough idea about this placement of the center of gravity. ගුරුත්ව කේන්ද්‍රය දල වශයෙන් කොතනයිද කියලා හොයාගත්තා නම් ගොඩාක් questions through අපිට survive වෙන්න පුළුවන්. Clear? Okay. Now a different question. Question number 6. Question number 6. It's like this. There's a table like this. Something like an umbrella is placed like this. Now, in a situation like this, it's quite complex, right? Why? Attention. You don't have enough data. Okay? Attention. In a situation like this, find the center of gravity of this umbrella or something like that. Okay? Now, it's quite complex. Why? There are no values to do any kind of a calculation. Clear? There is no value to do any kind of a calculation. සුළු කිරීමක් කරන්න දත්ත නැහැ. Due to this shape, it's difficult to have a rough idea about the center of gravity, right? If it is a rod like this, we know that the center of gravity is at the middle, right? නිකන් දණ්ඩක ස්කන්ධ කේන්ද්‍රය මැද්දෙන් කියලා දන්නවන්නේ. If it was a rod, we know the center of gravity is at the middle, right? I mean, if it was a plate, we know that the center of gravity is at the middle. Why? By common sense, right? We know to balance a plate, we should place the finger in the middle, right? Clear? So for common objects like this, we know. But due to this shape, it's difficult to have a rough idea about the center of gravity. Clear? And you don't have enough data to do a calculation. In such cases, you have to think a little bit further. Okay? You have to think a little bit further in such cases. So what should be the answer here then? What should be the answer here? In a situation like this, you can use your common sense. I mean, not common sense, basically for knowledge about equilibrium. සමතුලිතතාවය ගැන තියෙන දැනුම. I'm just here I'm explaining. In A level, as I said, you get a lot of center of gravity questions. Okay, in some cases you can do a calculation. සුළු කරන්න පුළුවන්. In some cases you can have a rough idea, but in some cases you have to think little bit further. Here, best solution is your center of gravity must be in this line. Your center of gravity must be in this line. That is the idea. Why? This system is balanced by two forces only. Clear? This system is balanced by two forces only. What are the forces? Here you have the normal reaction by the table. Clear? You have a normal reaction by the table. Table එකෙන් උඩට අභිලම්භ ප්‍රතික්‍රියාවක් දෙනවා නේද? Clear? So for this system to be in equilibrium, if the weight of this one is mg, for this system to be in equilibrium, R must be equal to mg. R must be equal to mg, and R and mg must be in the same line, right? Why? If there's a system where its weight is here, mg is here, R which is equal to mg is here, what will happen to this system? This is mg, this is mg. That means it creates a couple. Here you have mg, here you have mg. This is the object. You can find a perpendicular distance between them. This creates a couple. So system will rotate. Clear? So for a system to be in equilibrium, those two forces, so for those forces to cancel out, okay, they must be equal in magnitude, but they must be in the same line. See, if you apply two forces like this, it will rotate. But if you apply two forces at the same point, same line of action, it will not move. So for this system to be in equilibrium, two forces must be in the same line. Clear? So its weight, attention, its weight and this normal reaction must be in the same line. Clear? So you can find its weight may be placed somewhere like this. So its center of gravity should be in this line. Okay. So in an A-level MCQ, what you would get is, you will get A, B, C, D, E, answers like this. All you have to do is use your knowledge about equilibrium, draw a line and find the point. Okay. Find the point which goes through this point. Is that clear? මේ ලක්ෂ්‍ය හරහා යන රේඛාව හොයන්න. Clear? Is that clear? That is the basic idea here. Okay. That's how you find the center of gravity in this situation. You don't have a general idea, you don't have enough data to calculate, but you have an idea about equilibrium. Clear? සමතුලිතතාවය ගැන අදහසක් තියෙනවනේ. Clear? That's how you find the center of gravity in this situation. Is that clear? Is that clear? So you have to use different methods, okay? Different methods in different situations, okay? Write this down. Clear? Is it clear? Yeah. Okay, question number 9. Question number 9. And again, attention. Now, see, I marked center of gravity here, right? Why? I mean, I don't know exactly, okay? It may be somewhere here, okay? And again, please know this, center of gravity should not be on the object, okay? It's not a requirement, okay? It's not mandatory, okay? Someone can question, how can the center of gravity of this system be here? It should be on the object. There's no such requirement. Why? Consider a ring. This is a ring. Okay? Where can you find the center of gravity? Where can you find the center of gravity of this ring? Definitely at the center, right? Definitely at the center. Clear? There's no other way to balance this ring. Why? Its center of gravity is here. Gurutva kendra inne metana. After the proper calculation, you will always get the center of gravity here. So, center of gravity, it's not necessary to have the center of gravity on the object. Clear? It can be anywhere. Okay? It can be anywhere. Clear? Okay? That's why I marked it here. And then how can you balance this ring? There's no way. Okay? It's difficult to balance this ring if it is like this. You definitely, if you can connect two strings like this, and if you can place your finger here, then it will be balanced. Clear? Otherwise you can't balance it like this. Is that clear? Okay? So center of gravity can be anywhere. But there's something like this. Center of gravity can never stay out of the boundary. Boundary in the sense, if there's a object like this, okay, there's a certain boundary that it creates, right? Like this. There's a certain boundary that it, consider that this is a wire. This is a wire, metal wire. There's a certain boundary that it creates, right? Center of gravity can be on top of the wire. It can be here, anywhere. But it can't be here or here, something like that, okay? Usually it should be inside the boundary. So here also, in this situation also, there's a certain rough boundary that it creates, right? Rough boundary, I can't draw that properly. There's a rough boundary. It should be in that boundary. This center of gravity can't be here, right? Why? There's no mass in this side. So definitely your center of gravity can't be here, or here, okay? And it can't be here. So it should be in the boundary, but it need not to be on top of the object or something like that, okay? There's no such requirement. Object එක උඩ තියෙන්න ඕනේ නැහැ. Shape එකේ boundary එක ඇතුලේ හිටියා නම් ඇති. Clear? Okay? I'm emphasizing these parts because you usually get at least one question from center of gravity. That's why. To find the center of gravity. Question number 9. 1, 2, 3, 4, 5. So the system is like this. Where can you find the center of gravity of this system? I can use different methods. Attention. I can use different methods. I'll consider these 4. Where can you find the center of gravity of these 4 blocks? Where can you find the center of gravity of these 4 blocks? Definitely at the center, right? Okay. Definitely at the center like this. Is that clear? These 4 blocks. Where can you find the center of gravity of these 2 blocks? May the center of gravity? At the center, right? Clear? For uniform objects, center of gravity is at the center, right? Clear? Now, if mass of one block is m, 4m is centered here, 2m is centered here. Now, where can you find the center of gravity of the whole system? There's 4m here, 2m here. Center of gravity must be in this line, okay? Center of gravity must be in this line, more towards 4m, right? Close to 4m. So it will be here or here, somewhere like this, close to 4m. Is that clear? Clear, everyone? Okay. So in this question again, you need only the rough idea about the center of gravity. Okay. So for some questions you can do the calculation. For some questions you can get the rough idea. Okay. It depends on the question. Okay. And nobody cares how you get the answer, because many of these questions are MCQs. Okay. You have to somehow figure out the answer. That is the case here. Clear? Okay. Okay. Now, and what is more important about something again very important about center of gravity? Okay, write this down. Anything you have to write, I'll give 5 minutes. Write these things down. I mean, you don't have to write these things to understand, but whatever you need to write down, just write them. I'll give 5 minutes. Question? There's a question like this. Why can't I take this answer? Attention. For this one, I said that center of gravity should be in this line. Clear? Attention. I said that the center of gravity must be in this line. Clear? Attention. This line. Question was, why can't it be this point? Point A. Yeah, it's a possible answer. Okay, it's a possible answer. Why? Center of gravity is in this line. I can't exactly tell where it is. Okay, so A is also a possible answer, but I still an answer like this. Why? There's a lot of mass in this side. Okay, I mean, if you talk about the center of gravity is close to the higher mass, right? I mean, if you have a system where 100 kilograms is, you can find 100 kilograms here, 2 kilograms here, 3 kilograms here, 4 kilograms here. If you have a system like this, center of gravity of this system will be really close to 100 kilograms, right? Okay. So center of gravity moves towards the higher weight, right? Clear? So if the weight is equally distributed like a plate or a rod, then you can find it in the middle. Okay. So when you consider the attention, when you consider the mass distribution of this system, I feel that center of gravity should be little bit lower, because there's a lot of mass in this area. Clear? There's a lot of mass in this area. Clear? So center of gravity should be at least a little bit lower. Clear? Why? When you have this much of mass in this area, you can't tell that center of gravity will be here. Clear? Okay. From my point of view, it should be closer to this one and this part also. Why? There's a lot of mass here. Okay. And you know from experience, if you have a pen like this, it will be roughly balanced at the center. But if you connect a clip here, okay, to balance it, you have to take your finger really close to this point, right? To clip. Why? Because higher the mass, center of gravity moves towards that side. So from my point of view, in this question, there's a lot of mass here. So center of gravity can't go this high. Clear? See? That's how you reason. Okay? I can't tell that exactly the answer is this. Okay? We don't have enough data. But my rough idea is that it can't be here. It should be in this line, little bit towards this side. Clear? Not a very nice reasoning process, just a rough reasoning process. Okay, since we don't have values, we can't do a very correct reasoning process. We can't have a calculation or anything like that. Clear, everyone? Okay, so let's continue. So now again, there's something very important about center of gravity. Attention. In force and momentum lesson, okay? In force and momentum lesson, we learned a lot of theorems, like something is momentum conservation, okay? Things like momentum conservation. We learned a lot of theorems, right? All these theorems were talking about the center of gravity. That means, can you remember Newton's second law? What is Newton's second law? Newton's second law tells that Newton's second law mentions when there is no external unbalanced force. Oh, let's talk about Newton's first law. What is Newton's first law? When there is no external unbalanced force, system will remain stationary or it will move at a constant velocity. Clear? When there is no external unbalanced force, system will remain stationary or it will move at a constant velocity. Can you remember Newton's first law? But now you consider a bomb. There's a bomb here. Okay? Now this thing explodes. Okay? This thing explodes. And we said that when there are no external unbalanced force, system will remain stationary. And this explosion is entirely an internal thing. This explosion is entirely an internal thing, right? No external force. But still, it creates a motion. It creates a motion, right? Then how can we tell that? I mean, it will break into two parts and they will move. So Newton's first law states that when there are no external unbalanced forces, a system will remain stationary. Clear? But in an explosion like this, it is entirely an internal force, nothing external, but pieces moves. Then what happened to Newton's first law? What happened to Newton's first law? Okay, internal force but movement. Okay, there's something off with Newton's first law, right? No. There Newton talks about the center of gravity. Newton talks about the center of gravity. So that means, although this system moves, since there are no external unbalanced forces, initially center of gravity of the system was here, still center of gravity will be here. Still the system center of gravity will be here. Clear? So Newton in that law, in Newton's first law, he was talking about the center of gravity or the center of mass. Clear? Now we are correcting the theorems that we already learned. Okay? Okay. We are filling the gaps actually. Okay? Because in an explosion like this, it looks like Newton's first law. There's a problem with Newton's first law. No. Newton talked about the center of mass. That means when there are no external unbalanced forces, center of mass of the system will remain stationary. Clear? Skandha kendraya තමයි එක තැන ඉන්නේ. Clear? So no matter how far its pieces move, center of mass will remain stationary. Skandha kendraya එක තැන ඉන්නේ. Clear? Is that clear? So this concept and principle of moment now makes our calculations and some questions really easy. How? Can someone tell me what is the moment around the center of gravity? 0, right? I mean, if the center of gravity of this system is here, if you consider the moment Gurnaya around this point, if you consider the moment around this point, what will be the moment around this point? 0. Why? As we know, now there are two ways to find the moment. You can take each force and get the moment and add them. But according to principle of moment, this sum of moments is equal to the moment of the resultant. Can you remember? According to principle of moment, Gurna Mula Dharmeta anuwa, okay, according to principle of moment, total moment is equal to the moment of the resultant force. So in a rod like this, its resultant weight acts from the center of gravity. Clear? Its resultant weight acts at the center of gravity. Clear? So to get the total moment, what can I do is, I can consider the total weight and take the moment by the total weight. Can you remember? Principle of moment mentions you can get the sum of moments or you can get the moment of the resultant force. You will get the same answer. Clear? Okay? That's what principle of moment mentions, right? So if you get the moment around the center of gravity, you will get total weight is mg, distance is 0, right? Distance from center of gravity to center of gravity is 0, right? 0. So resultant moment is 0. So there is no resultant moment around the center of gravity. I mean, it's obvious, right? That's why it doesn't rotate when you place your finger at the center of gravity, right? Clear? So initially, if they mention something like this, you have 4 kilograms here, you have 6 kilograms here, okay? If an explosion happens, they move in certain velocities, and this 6 kilogram piece moves 4 meters. Then if they ask you the distance to the 4 kilogram piece, initially you have to apply momentum conservation, Gammeta Sansthitiya. Then you have to find V1 and V2. Clear? After finding V1 and V2, you have to calculate the time taken to move 4 meters. Then using that time, you have to find the distance that 4 kilogram will move, right? Initially it was like that, right? First you have to apply principle of momentum conservation, Gammeta Sansthitiya දාන්න. Then find velocities, then find distance. Clear? Initially it was a little bit difficult, but now what you know is, now you are not going to apply momentum conservation. Gammeta Sansthitiya දාන්න යන්නේ. We are just applying Newton's first law. What is Newton's first law? When there are no external unbalanced forces, system will remain stationary. Clear? බාහිර අසන්තුලිත බල නැති වුණාම පද්ධතිය මොකක්ද වෙන්නේ? නිශ්චලයි. System will remain stationary. That means its center of gravity was here initially. Its center of gravity is still here. Clear? So now I'll consider moment around center of gravity. Attention. I'll consider moment around center of gravity, around O. I'll take this direction. Attention. Now, 6 kilograms into 4. It's towards this side. Here 4 kilograms into x, it's in opposite direction. So minus 4 kilograms into x. Minus 4 kilograms into x. 6 kilograms into 4 minus 4 kilograms into x. What is the moment around the center of gravity? 0. ගුරුත්ව කේන්ද්‍රය වටේ ගූර්ණ බිඳුවයිනේ. Moment around the center of gravity is 0. Now what do you get? X equals 6 meters. Clear? X equals 6 meters. Now many of the questions that we did earlier, clear? Using momentum conservation. Now these questions are really easy. Why? Momentum conservation means applying Newton's first law to the center of gravity. Is that clear? ගම්මිතා සංසිතිය කියන්නේ නිව්ටන්ගේ පළවෙනි නියමය ගුරුත්ව කේන්ද්‍රයට දාන එක. Clear? Okay. I'll give you a question. This thing will appear in your, I think, paper or revision tute. There's a frictionless system like this. There's a frictionless system like this. It's placed on top of a frictionless plane. Attention, it's placed on top of a frictionless plane. Weight of this one is 10 kilograms. You place a small ball here. Small ball here. Its weight is 5 kilograms. Okay. This is a hemisphere. Ardhagolayak. Its radius is 10 meters. There's no friction anywhere. Clear? Okay. And this thing will not move. Let's make it a little bit like this. Now it's not exactly an hemisphere. It will not move like that. Okay. Okay. Or else let's go with the initial question. It will not oscillate. Okay. It will not oscillate. That means it will only move horizontally. It will not move like this. Clear? Now, when you release this system like this, what would happen? When you really, or else you can talk about the friction. Yeah, you have friction here. You don't have friction here between the flow and this object, but you have friction here. Between this one and this one, you have friction. Now, what will happen? It will move like this. Then like this. Like this. Due to friction, it will slow down little by little. Clear? Then it will move like this and eventually it will stop here. Is that clear? Is that clear? When you place it here and drop it, it will move like this, but it would decelerate due to friction little by little, and finally it will come to a rest at this point. Is that clear? Now tell me, this is a ball. How far this ball move throughout this motion? My question is, when this thing moves like this and when it reaches this point, this one will move horizontally. Okay? What is that distance? What is that distance? If you need, you can consider mu as friction coefficient as 0.4. Okay, so if there's anyone who's new to this lesson, who haven't learned this lesson, please wait today and ask for the recordings. Okay, you can get the recordings. Or anyways, even if you are comfortable with previous theory parts, just get the recordings. Then Whenever you are doing the paper, if you find anything difficult, you can watch my recordings. Okay, so the plan is every week there will be a paper today. I mean, every Wednesday I will release the Wednesday class paper, as I explained last week. Every Thursday I will release Sunday class paper. You can write the Wednesday class paper or Sunday class paper, or if you like both. Okay, that is the plan. So even today after the class, if you like, you can write the paper. Try to find the answer quickly. There's friction here. There's no friction. This flow is frictionless. It's a frictionless flow. I'll make it a little bit easy. Let's make this one not 10 kilogram. Let's make it 5 kilograms. Let's make it 5 kilograms. So this ball is 5 kilograms. This pebble is also 5 kilograms. Try to get the answer. How far will this ball move? Yeah, talking about the horizontal distance. I mean, when the pebble is moving, the ball will move like this, right? Horizontally somewhere. Okay, I need to find how far will it move at the end of the day. මොකද? So some students hasn't been able to do the model paper 1. So if you like, now you have model paper 1, 2 and 1 and 2 both there today. So if you like, you can do both, okay? If you want, you can do both papers, model paper 1 and 2. And you don't need, I mean, it's not a must to write it today, okay? If you like, you can come to the institute tomorrow and write. If you, don't start the paper after 5 or 5:30 p.m. because institute will be closed around 6 p.m. So, you any other day from maybe around 9 a.m. to 3 p.m. you can start a paper here, okay? You can just come to the institute and request the paper and do the paper at this hall. Okay, not this one, the next hall. It's a very small concept that you have to use, okay? A very simple concept. Huh? And these days, like one very common question, like term test lakunu madi. So not enough marks for term test. I mean, it's quite obvious, right? So term test marks, I mean, yes, I always explain, especially for Sunday class students, from the first day I asked them to get like highest possible marks for first term tests, but it's your life easy, right? Okay, if you were the class first or section first in the first term test, now, I mean, class teacher will not bother you. I mean, class teacher will not even think about you. Okay, you can come to the class if you like. You don't need to go to the class if you like. I mean, I have explained you, right? Those days, I mean, first term test, I was the section first at my school, Ananda College. So after that, I mean, even for the first time, I didn't go to the classroom because I have practices and all. But I mean, after that, nobody cares. Okay. In the first term test, I mean, in the first term, I wasn't able to go to the class for around 2 months. Okay, because of the tournament season, you know the issue, right? Tournament season starts, and you are not able to go to the class when in this tournament season. So even our section head called and asked my parents to move me to art section. Okay, even like our section head called my parents and asked them to move me to the art section if I'm not going to learn. So it's all about, for me it was all about surviving in the section, because if I was not going to get good marks, I would be doing art. So but I had a good confidence, because I mean, I did learn in classes, I mean, very well. So anyways, I got very good marks in the first term test. I think I was the section first from a lead around 30 marks. Okay, it's just 3 subjects, and 30 marks lead means a huge lead. So after that point onwards, I'm not going to, I never went to the classroom. Okay, and I mean, nobody cares. Okay, even the class teacher doesn't care. And I mean, even the class teacher, when I have practices at the ground, in the morning he come to the ground and check whether I'm there, because he can mark present. Okay, he don't care. I mean, these teachers are not rude. Okay, usually one common problem for the people who do sports is there's a huge resistance from teachers, right? There's a very huge resistance from teachers. Why? I mean, they don't allow you to do anything, right? I mean, it's really, I mean, they are doing their job. Why? They have seen like hundreds or thousands of students who fail by doing too much sports. Okay, that's their normal experience. So they are frightened that you would go in the same path. That's why they are resisting. Okay, that's why they don't let you go out. Okay, that's why they don't let you do your practices. Otherwise, they will get their salary anyways, right? Okay, they don't have to think. So they are afraid because they are good. Okay. So what you have to do is you have to just get good marks at the term test. Then they will not care, because they know that anyhow you are going to do what you have to do. So they won't care. Okay. So my class teacher was really cooperative after that. Okay. I mean, I can give him a call and tell for the next 2 weeks I will not be able to come to the class because I have tournaments. So please mark present, and it's all okay. I have present. I mean, I get present for whole 2 weeks. Even for a month, no big issue. Nobody cares. Why? They are not rude. Okay. If you can give them that assurance that you are going to get marks, even though you come to the class or not, they don't have to be worried about you, right? So getting good marks in the term test is really important. Okay. Why? It gives your teachers a certain assurance about yourself, so they don't have to think. Okay. Then they don't have to think about you being there or not, you going for practices or not. Okay. They don't care after that point. Okay. So I always ask all the students, try to get good marks at the term test. It's really beneficial. Okay. Okay. Even when you are the class first, everyone in the class usually bring you the difficult questions, right? So I mean, you will get a collection of difficult questions every day. Without doing, after getting good marks, and if you become the class first, you don't have to go do a lot of papers and find difficult questions. Why? Anyways, the people will bring all the difficult questions to you, right? If you are the section first, the section will bring the difficult questions to you. So the life becomes really easy if you get good marks. Okay. This is applicable for class first, second, third, fourth, everyone. Okay. The life is really easy if you can go for good marks. So go try that. Okay. But it's not necessary. Okay. It's not necessary to do it in the first term test, because as I mentioned this before. As I said, I was the class first. Okay. Our class second is the island first. Okay. I was the class first. Our class second, Tarusha, is the island first. Okay.
first term, second term, third term, and fourth term, I was the class first. And I can't remember about the fifth term. And in the sixth term, Tarusha was the class first. So, I mean, for 4 or 5 terms, I was the class first. But we had our class second is island first. Okay. So, in the first term, I can remember for maths, I had 88 or something like that. And Tarusha had 30 something for maths, okay? I'm talking about the island first, okay? So, your first term test marks doesn't matter. It doesn't decide your final marks, okay? But what about talking about Tarusha and me is, I was always there. First term test, I got 88. And even in the last term test, I was still at 80s because my target was to, barely survive in A-levels because I had a lot to do other stuff, okay? But for Tarusha, he was always aimed about going for a good rank. Not specifically a rank. He always wanted to get good marks, improve. So he was constantly working. Every week, every day, he would try difficult questions. And whenever he get low marks, he would collect some papers from me. Okay, get some papers from the teachers who taught me. He would collect my papers. He would get tunes from other students, and he would try them, and he would try to improve. He would get notes from other students and read them. Likewise, his story was like he was always improving. So we saw the result. Okay, we saw the result. His island first, and his Z score, it's 2019 A level. His Z score was huge, 3 point something. Okay, 3 point something Z score means a huge Z score. Okay, usually island first people get 2.8 Z scores, 2.9 Z scores. I'm talking about the person who got 30 something in the first term test. Okay, so first term test marks doesn't matter. It's really good if you can get. Okay, but it doesn't decide your A level marks. Okay, for A levels, what you need is persistence. Okay, if you can keep working. Okay, attention. If you can keep working, keep improving. Okay. And if you can learn from everyone, it's something good about Tarusha is he tries to learn from everyone, even further. He's the class second, but even from, class 25th, 26th, 30th, he would get some papers from them. He would ask questions. Okay, he was learning from everyone. So if that behavior, if you don't have that ego, okay, if you don't have that ego. If you are ready to learn from everyone, if you are collecting papers, if you are doing questions, and if you are ready to go and ask questions from the last person in the class, if you are willing to learn from everyone, then we can guarantee about 3 years. Okay, it's so the 3 years comes as a result. It's not about your IQ. It comes as a result of your attitude. Okay, just try to understand. Some people, they become class first, second in first terms. Okay. Then they think they are Einstein and Newton. So they don't work properly. Then we have seen people failing, class first people failing A levels. Okay, we have seen that. Okay, so it's all about attitude. Okay, if you are ready to learn always, if you are ready to improve always, it's all about improving every second. That means if you take Tarusha, I'm not a good example I wasn't improving at all, okay? I was there, okay? Always I was there. My marks were steady. My marks were like this, okay? That's all I needed. And Tarusha's marks were like this, okay? That's how our marks varied in term tests, okay? So, if we talk about this guy, this is not a good example. Okay, if we talk about this guy, it's all about continuous learning. Attention, Tarusha would, he would check for everything. If a teacher tells that your handwriting is not good, next day his handwriting will be good. Okay. If he feels like if he did a lot of careless mistakes in a certain area, next day he has figured out a method to get rid of that. Likewise, it's quite different. His attitude was quite different. What he tries always is to improve something. Maybe handwriting, simple stuff like handwriting or attention. Okay, or like MCQ speed. Likewise, he always try to improve at least a small thing. Okay, even in this class, if someone tells you that your handwriting is difficult to read, you don't care, right? That is the problem with the attitude. Okay, but if someone tells us, even me, that your handwriting is not good, I take it serious and I check whether what can I do about that. At least improve it a bit. Okay, that is the attitude. If you are going to be be great in anything, that is the attitude, okay? If I tell someone that you are not focusing enough, okay, I mean, you won't care. That day you will not speak, but you won't care, right? But if someone tell a person like this that you are not focusing enough, he would evaluate and check whether, okay, I'm actually not paying attention. There may be a huge impact from that. So he he go and search what are the methods that I can improve the attention. That continuous learning, continuous improving, that attitude brings huge amount of marks, okay? It's not your IQ, okay? For me, I have survived throughout my life from IQ, I think, okay? Because Olympiad, I got the gold medal. Tarusha had a silver or bronze, I think. Why? Olympiad, you can't win by discipline. Olympiad, you need IQ, okay? But, I mean, A-levels, it's all about discipline. It's all about discipline. Engineering, both. We are both are doing great in engineering, I think. So that's the story, okay? First term test marks matters, but it doesn't decide your A-level marks if you are a kind of person who learns continuously. But the problem is many people don't learn continuously, okay? They don't care if someone tells that your handwriting is not, they don't care. If someone tells that your maths, you could have improved your maths marks, okay? If you are class first and if class sixth come and tell that you should have done this question this way, මොකද හිතන්නේ? මොකවද මට උගන්වන්න? Okay? So that kind of attitude, it destroys people, okay? Not the IQ, okay? So the most important thing, if you need a curve like this in your marks, it's the attitude. It's the attitude that you must be willing to learn from everyone and always, clear? So work on that, okay? You don't have to work on your IQ, it's impossible, okay? You have to work on your discipline and attitudes, okay? It's really important, okay? No matter what you are doing. Okay, I'll explain this question, attention. So, again, it's simply Newton's first law. Newton's first law. Newton's first law states, what is the updated version of Newton's first law? What is the updated version of Newton's first law? When there is no external unbalanced forces, center of gravity of the system will remain stationary, okay? Now, you have 5 kilograms here. Where can you find the center of gravity of this ball? Since it is symmetric, you can find the center of gravity in this line, right? You can find the center of gravity in this line, clear? Here you have 5 kilogram and this is 5 kilogram. So this 5 kilogram is placed around here, right? So you have 5 kilograms here in this line, 5 kilograms here in this line, and in which line can you find the center of gravity of the whole system? I'm talking about the x distance of the center of gravity, okay? X distance of the center of gravity, you have 5 kilogram in this line. This 5 kilogram in this line, where can you find the center of gravity of the whole system? At the center, right? Because if you have 5 here and 5 here, where can you find the center of gravity? At the middle, right? At the middle. Is that clear? So center of gravity of the whole system will be on this line. Clear? Okay? Is that clear? So that means, since this is 10 meters, this is 5 meters, and this is 5 meters. This is the center of gravity of the system. Clear? Now, after some movements, this pebble reaches here. This pebble reaches here. Clear? Now, where can you find the center of gravity of the system? 5 kilogram is on this line, this ball, and this 5 kilogram is here. So definitely 5 kilogram, the center of gravity of the whole system is here, in somewhere in this line, right? Clear? Okay. So initially, So initially center of gravity was here in this line. When this thing moves and when it becomes stationary, center of gravity of this whole system is here. Clear? But according to Newton's first law, center of gravity can't move without external unbalanced forces. Without external unbalanced forces, center of gravity can't move. Clear? So, your center of gravity can't move from here to here. So, when this thing moves and when it becomes stationary, this place should be moved to this place. That means when the pebble becomes stationary here, this system will move up to this point, so that center of gravity is not changing. Initially center of gravity was here, now still the center of gravity is here. Center of gravity can't move without an external unbalanced force. Clear? බාහිර අසන්තුලිත බලයක් නැතුව ගුරුත්ව කේන්ද්‍රයට යන්න බෑ. Clear? So this thing will move up to this point. Clear? That means it will move a distance of 5 meters. Clear? So the center of gravity will move 5 meters. Is that clear? Clear? So initially, to do a question like this, you have to apply maybe momentum conservation, find velocities, total distance traveled by the pebble, then the total distance traveled by the ball. Okay, it's a huge task to find the movement of the ball. Okay, but now with the concept of center of gravity and with the updated version of Newton's first law. What is the updated version of Newton's first law? When the external unbalanced forces, center of gravity of the system will not move. ගුරුත්ව කේන්ද්‍රය කොහෙවත් යන්නේ නැහැ බාහිර සන්තුලිත බල නැත්තම්. Now it's quite easy. I mean, you can calculate the whole thing in your head, right? You don't have to write anything to get this answer, right? Answer is just 5. Okay, clear? Write this down, and we have to do more questions from moment, and again from couple of forces, principle of moment, center of gravity. We have to do more questions. Okay, today I didn't do much. Okay, so attention, finish all the questions up to exercise 8. Exercise 8 we have to do more, because exercise 8 will be difficult. Other questions in exercise 8 will be difficult. So finish exercise 1, 2. These are really easy exercises. Okay, 1, 2, 3, 4, 5, 7. Not 7. We didn't learn this. Attention. We didn't learn this content. So you can't do exercise 7. Again, exercise 8. You can try up to question number 12. Exercise 8 up to question number 12. Try these questions, and next week I'll start by doing lot of questions from this area. Okay. Today we learned only theory. Next week we have to do more questions. Okay. Exercise 1, 2, 3, 4, 5, 6. Not 7, 8. Exercise 8 up to question number 12. Okay. So if you didn't understand any concept today, don't worry. Next week you will understand them after we do a lot of questions and get the revision. You got the revision tube, right? For online students, I'll upload that to the group. And you have the model paper 1 and 2 both available there. Okay. You can write it and hand over to the institute, or you can upload it online to the link that we provide in the group. Okay. So that's all for this week, and thank you.
Recording stopped.